from Nitronics, and welcome back to my video tutorial series on getting started with FPGA design using Xilinx's Vivado tools and Digilent's RDZ7 FPGA development board. So far, we've looked at how to install Vivado Vitis 2021.1 as well as getting up and running in Vivado 2021.1 by creating a base reference design for the RDZ7. We left off where we had last created our HDL wrapper for the design to actually instantiate it. So picking up right where we left off, we're at a point where we're ready to start actually compiling the FPGA design, what that means, there's 3 different steps to that. The first step is synthesis, which is actually where your HDL code, the IP blocks, the HDL code that makes those IP blocks, that is actually taken by the Vivado toolset, or honestly whatever toolset you're using, because synthesis is the first step in any compiling, and whether you're using Microsemi or Intel or Vivado, it takes all of that and actually translates it into logic level configurations, actually configuring the logic gates on the FPGA itself. Then after synthesis, you run place and route, where it takes those logic gate configurations and actually implements them on the physical gates of the specific FPGA you're targeting. So that's where you start to see things like your timing, if your design is too complex or poorly laid out, the logic gates that need to communicate with each other too far away, so you'll get timing violations and things like that. Then finally, the last step is creating a bitstream in the overall process. So a bitstream is where the actual information from synthesis and place and route have been taken from, and it's actually generated into a final file, bitstream file that is used to actually program the FPGA when it is powered on. For Xilinx specifically, it's an actual .bit file. There's several other file extensions you can see. I think there's one of them that calls it programming data. I think that might be Microsemi, but overall, whenever you pick up a new FPGA development IDE, you can guarantee you'll have those 3 overall compilation steps of synthesis, place and route, and bitstream generation. In Vivado specifically, place and route is actually called implementation. So now that we have our base design ready and developed, our first step here is going to be to run synthesis. We're going to look in our flow navigator, and you'll see we have our run synthesis option. So let's go ahead and click on that. Now, depending on how complex your design is and how big of an FPGA and how full it is, that can cause these different steps to take varying amounts of time. For a Zinc 7000 such as this and a super lightweight design where we've just got the actual Zinc IP and some GPIO, the synthesis shouldn't take too long on this. But once we get running here, we can take a look at our design runs and kind of see what our status is. So we're queued up right now. So for the block design, it actually does run synthesis for each of the IP blocks. So like I mentioned before, each of the IP blocks are comprised of underlying HDL code, whether that be Verilog or VHDL. So each one of these IP blocks you see in our block design, those have to have their own synthesis run to convert their HDL code into actually logic level gate configurations. So as you can see, that's what we're waiting on. So it looks like it's running on the processor system reset. It finished that. The clock wizard, the Axie GPIO, those have all been synthesized. It looks like it's moving on to our actual interconnect, and then the Zinc processing system itself, which there's not a lot of HDL code that's actually configuring the Zinc processor itself, since the Zinc processor is a physical ARM core instantiated within the FPGA, but there's all of the HDL code around it actually connecting the fabric to the Zinc processing system, which that's what this synthesis is running right now. Maybe a little bit more detail than you care to know, but it's always kind of good to have an idea of what your FPGA IDE tools are doing at the time. That way it kind of helps you with troubleshooting. Or you're just a weird, curious person like I am. So it looks like we've run synthesis for all of our blocks within the block design. So it started running the overall synthesis design for the project. So like I said, you can see that didn't take very long. It's all very simple IP blocks, and I've managed to talk through it all. Does anybody else, since you've been in quarantine by yourself, do you suddenly find yourself, when you talk to a person, you suddenly can't stop? I feel like I've had a lot of eyes glaze over at me where it's like, oh, stop talking, you're giving me too much detail. I've been alone in an apartment for a year and a half now. All right, so there is our synthesis complete. So when Vivado completes its synthesis, it pops up and gives you a few different options of what to do next. You can either just take a look at the reports that were generated back as far as stats on the synthesis. You can open up the synthesized design, or you can jump straight into running implementation. Because this is a brand new design, we're going to jump into opening the synthesized design because there's a few things we need to do here. So I'm going to choose Open Synthesized Design and click OK. So that'll take a moment.
A few moments later.
So as you can see here, it'll open up our package device view. It looks like the default view that opens is I/O planning. But there's a few different things where you can either do I/O planning, which is where you're actually choosing what signals from your design go to what specific package pins on the FPGA. You've got floor planning, debug, timing analysis. So we're going to stick in I/O planning, and then in the device you can actually see all of the sectors available within the Xilinx Zinc 7000 FPGA. So we've got a few different banks here. So it is worth noting in the Zinc FPGAs, all the different banks have their own voltage rails connected to them. So if you have a certain voltage rail set on a particular bank, all of the pins have to operate at that voltage. So if you set that voltage rail for bank 14 to 3.3 volts, all of your I/O connected to those particular pins connected to voltage bank 14 all have to operate at 3.3 volts. Because we have our design synthesized, we don't actually have any of our constraints in yet, since this is a brand new design. So there's a couple different ways that we could add our constraints, which are I/O planning, which we'll need for our actual place and route, since our place and route or implementation, since implementation is actually taking the configured gates and laying them out in the specific FPGA, it does need to know those endpoints of where it's going. So we're gonna go ahead and stop in the synthesized design to add the actual pinouts for the designs. So you can either do that all by hand from this I/O planning view, and you can take a look. Most everything is normally connected. In these designs, when you have a default design, especially like all the DDR, that's all hard routed. That doesn't go through the PL, so that's already hard routed to the design. So you'll notice, it looks like we only have one thing here that's not connected, and that is our reset port. So to know where that is, we can go back over to Digilent's support page. So if you start at the Digilent support page, there's the master XDC files. So the constraint files for Vivado FPGAs are .xdc. So if we go to the XDC, that'll take us to their overall constraints for all of their boards here at Digilent. So we're using the RD Z7-20. So I've already got that open here. So we're just gonna search for where does the reset go. So it doesn't look like I have a specific reset pin, so I can choose to connect it to one of my buttons here. So it looks like we have some sort of software reset. There is a button for reset, so let's see if we can find that in these constraints. So it looks like I'm just gonna go ahead and connect. It looks like this software reset is just connected to the general reset. It's not connected to any of our package pins available to us. So let's see if we can use one of these other buttons. So I left these four buttons unconnected here I'm currently not utilizing them, so I think I'll just go ahead and use button 0 as my reset line. If I take a look and see where button 0 is, that is on package pin D19. So I'm going to come back here, and on my reset RTL, I'm going to click D19, and it looks like that is IO standard LVCMOS 33, so that means that bank is tied to a 3.3 volt rail. So this is another thing to keep an eye on FPGA development boards, and one of what I guess you could call a downside to using an FPGA development board for is a lot of the times the voltage rails are tied to a specific value. They're on the PCB. It's not as common to have those voltage banks be configurable. Some development boards do have it to where you can change jumpers and change what the power supply is actually setting those rails to. So if that's something that's important to you in your design development, or you're proving, because typically you're using an FPGA development board to smooth out a design that's ultimately going to lead to your own custom FPGA layout board. Be cognizant of that. If you care about setting your own voltage rails, make sure that take a look at the schematic of the development board you're looking at. Make sure that you can do that. The RDZ7 is not a board where you can set those, so those are all hard routed to specific voltage rails. So that means we need to change the IO standard to LVCMOS 33, and then we can hit save on the synthesized design. And it's just getting a warning that because we are making changes to the synthesized design, it's going to push the design out of date, meaning we're going to need to rerun synthesis. Because we haven't created a new constraints file, or we don't have an existing one in there yet, this is just prompting us to go ahead and create a new file, or if we had an existing one we wanted to pull in, we could. Let's go ahead and create a new one. So I'm just going to call this RDZ7 pinout and local to project. Whenever Vivado wants to put something local to project, I normally just let it. I highly recommend doing the same. I've probably been using Vivado since its very first version, 2013.2, and I've kind of learned the hard way across all of those that if you mess with some of the local to project stuff, it gets weird because there's all kinds of underlying pointers that it has within the software. So click OK. So go ahead and you'll see it pushes our synthesis out of date. So we're going to go ahead and close the synthesized design for now and rerun it. So this should be pretty quick because we didn't actually make a real change where it needs to go in and change how it compiled any of the HDL code into actual logic level gates. So you'll see none of the actual block design synthesis went out of date. We're just rerunning that top level now that we have the constraints file in, and we've basically given the Vivado toolset a little bit more information about what the final design looks like. And while this is running, if you had more specific timing constraints you wanted to add, there's also the constraints wizard within the synthesized design. So let's go ahead and just take a look at that real quick. This design's pretty simple. We don't really need to worry about it, but just it's good to be cognizant of where it is. So we've completed another synthesis run. We've reopened the synthesized design. So if we open up constraints wizard here, what this does is let us do things like declare our clocks, declare specific input and output delay from certain pins. Sometimes if you have really tight timing on things and you know that you have, let's say there's an input pin and you have a external to the FPGA, you know there's a certain delay that it's going to take that signal to get there, you can configure that within your FPGA design such that your FPGA design gets laid out the most efficiently by the tool sets. So as you go through, you can kind of play with going through. You've got this first one where you're adding your primary clocks, other recommended constraints, I won't get too detailed into that, forwarded clocks, feedback delays. So input delays, this goes with what I was talking about earlier, where if you know that there's a specific delay of external circuitry that it has to go through, you can implement that here. Since I'm not putting anything in here, I'm just gonna go ahead and hit cancel. But if you were to add any of those in there, it would write all of those things to the actual constraints file. You could come back and rerun your synthesis again, just like we did earlier. Now that we've taken a look at the synthesized design and I've explained some of the tools within the synthesized design, also for those of you that were used to ISE, where you had the schematic view, you can also open the schematic view of your design from the synthesized design here, down from the flow navigator. So we're going to go ahead and close the synthesized design for now. So we're going to come down to implementation, which is what Xilinx calls the place and route stage. So we're going to hit run implementation. Go ahead and launch those runs. So since we're taking that synthesized design that is actual gate configurations and applying it to this specific Zinc chip on the RD board, you'll notice that when the implementation is running, it's just running one versus it's not running an implementation for every single IP block that was in the block design, the same way that we had to run a synthesis for every single block that was in the IP design. And again, like I mentioned earlier, since it's not a very complex design, it's pretty lightweight, you'll notice that implementation only took, I think, a couple minutes. And again, we have an option here of we can either open an implemented design, generate a bitstream, or view the reports. So let's go ahead and open the implemented design and take a look at what's in here. You'll see we've got our package and our IO planning view again. And we could, technically in implementation, you can run implementation without specifying endpoint constraints like we did. You could come back, place them here, but you still would have to rerun implementation again to actually get the proper, because overall, like when place and route is done, place and route needs to know where these final signals are going to go to on the package pins, because if you run implementation without specifying the final pinouts, it could place the design in some random part of the chip that's nowhere near the actual proper package pins, whereas when you go back and add the proper package pins, Vivado will recognize that and say, hey, all of the package pins are in this corner of the chip, let's implement and route the design over here in this corner of the chip. That's why I just like to go ahead and make it a practice of adding my constraints in the synthesized design. It just saves me an implementation run. So we've got our package, and then now under device, you'll notice we've got this highlighted section here in the middle. So this gives you an overall view of exactly how much of the actual FPGA, how many gates we're utilizing for design within the FPGA. Like I said, it's a relatively small design, so we're using a tiny little chunk compared to the rest of this. As your design gets bigger or more complex and you fill more of the physical gates in an FPGA, you'll notice you'll start to have things like you'll be more prone to timing errors just because things will be forced to be placed too far away from each other. You'll have issues with clock timing from high clock fan out because a single clock has too many places to go within the FPGA. So as a good rule of thumb, you want to size the FPGA that you purchase to not be the exact same size as your design. You definitely want a little bit of space, a little bit of wiggle room. It's kind of like your house. You don't want to buy a house or have an apartment where it just perfectly fits all of your stuff because then there's no room for you to move around, and you need something that's a little bit bigger than the amount of stuff you have so you can move around in it. Same kind of weird analogy. And we have no, like I mentioned earlier, we only have a few warnings and infos. We have no critical warnings, meaning our design meets timing and everything else. So because we have no critical warnings or errors, we can go ahead and move into our final phase of our FPGA compilation, which is actually generating a bit stream. If I wanted any sort of more detailed reports, such as an actual detailed timing report of how the specific time delays and everything, or if I wanted to see exactly how much power my design is consuming, Vivado has all these great reports that you can either take a look at a summary of or export a more detailed version of. So you'll notice that every time I go to move on to the next section, I do close. So like when I move on from synthesis to implementation, I close the synthesized design, and then when I'm moving on to generate the bitstream, I'm going to go ahead and close the implemented design. That's just kind of a personal thing that I've always done in Vivado. You can leave the synthesized and implemented designs open when you run the next step. I typically recommend going ahead and closing them just because it's more resources, more memory that Vivado is having to consume on your machine. I've also noticed that sometimes it can make Vivado crash if you have too much, like your block design, synthesize, implement, all of that open and you're trying to run another stage, so that's just generating a bitstream. So I recommend once you complete a certain phase of the compilation, go ahead and close that part of it. I still have the block design open. That's normally a little bit safer one that's not really consuming a ton of resources, but I'll go ahead and close that for now. And then we're gonna, our final step here is to go ahead and generate a bitstream. And like I said, the bitstream is the final compiled design into a single file. That file is what's going to be stored on the FPGA, whether that's in Flash or on an SD card, and that's actually what's going to be loaded onto the FPGA every single time it boots up, telling the FPGA how to configure its gates within it. So FPGAs, every time that they have power removed from them, they completely forget all of the logic configurations they had. So because FPGAs don't have any memory once power is removed, you do have to have some sort of external memory on the board, such as QPI flash or eMMC, to store that bitstream on, and then there's a whole boot sequence where the bitstream is loaded off of that external memory onto the FPGA every time it powers on. Again, our bitstream generated pretty quick, so we can go ahead and openly implement a design again, take a final look at exactly how much space our design consumed, which really doesn't change between your implementation and bitstream generation, which is typically why I just do view reports. You can open the hardware manager in Vivado, which the hardware manager allows you to go ahead and program the bitstream on the FPGA, and also look if you had any ILAs or logic analyzers instantiated in it. That's where you would also connect to those and be able to look at those, or generate your memory configuration file for programming your bitstream into Flash. So I'm just gonna go ahead and do view reports for now. So it looks like when I ran the bitstream generation, I did get a critical warning here. It looks like it says something about a board part definition was not found. So it looks like it's just something to do with the board preset file for the Arty board. Looks like it's missing something in particular. Because I think there was a lot that was overhauled in Vivado 2021.1 with how it handles the board preset files, and then I also saw that the Digilent board IPs may not be totally updated yet. I think it's safe to go ahead and ignore these critical warnings. I know typically I said don't do that.
Critical warnings you don't want to ignore.
But like I said, sometimes when you're an FPGA developer dealing with these tools and you're in a weird update state, sometimes these things happen. I think that's all for this tutorial for now. So just to recap, we've went through the entire FPGA compilation process, that this process is the same for any FPGA, whether you're using the Xilinx or Intel or whatever boards where it's your synthesis, your place and route, and bitstream generation. That was a demo in Vivado 2021.1. Bye.